The 24th of March 1945. An amphibious vehicle staging area near the Rhine River, western Germany. Maintenance crews completed final inspections on 284 six-wheeled amphibious trucks capable of carrying 2.5 tons of cargo or 25 combat-equipped soldiers across water obstacles without requiring specialized landing craft or bridge construction. Each vehicle measured 31 feet in length and weighed 13,000 pounds when fully loaded. Contemporary intelligence reports indicated that defending forces had not anticipated the deployment of wheeled vehicles capable of direct water-to-land transition during major river crossing operations. Supply officers recorded fuel consumption rates of 4.2 gallons per hour during water operations and 8.7 miles per gallon during road movement. American industrial planners had developed amphibious cargo vehicles that eliminated the tactical vulnerabilities associated with conventional river crossing operations, creating logistical capabilities that defending forces had not encountered in previous campaigns. This technological advantage enabled sustained supply operations across major water obstacles without requiring the construction of vulnerable bridge structures or the deployment of limited numbers of specialized watercraft. The resulting operational flexibility fundamentally altered traditional concepts of river crossing operations through integrated amphibious logistics capabilities. Industrial production records demonstrate the scale and efficiency of American amphibious vehicle manufacturing during the critical late war period. Factory output reached monthly production rates of 583 vehicles by early 1944, with total manufacturing exceeding 21,247 units across all variants during the complete production cycle. Assembly facilities operated on three-shift schedules, completing one vehicle every 4.7 hours during peak production periods. Quality control inspections maintained rejection rates below 2.1%, while meeting accelerated delivery schedules essential for operational requirements. Manufacturing specifications incorporated components from existing military vehicle programs, achieving parts commonality of 67% with standard truck chassis and marine propulsion systems. This standardization enabled rapid production scaling using established supply chains while reducing specialized tooling requirements. Component integration utilized proven automotive technologies adapted for amphibious operations, ensuring mechanical reliability under varied operational conditions while minimizing development time and production costs. The amphibious design philosophy reflected systematic analysis of river crossing vulnerabilities and logistical bottlenecks encountered during previous campaigns across multiple theaters. Engineering teams prioritized versatility and reliability over specialized performance characteristics, creating vehicles capable of effective operation on both land and water without requiring extensive crew training or specialized maintenance procedures. Design parameters enabled operation in water depths up to 7 feet, while maintaining full cargo capacity and crew protection under adverse conditions. Propulsion systems incorporated dual-mode capability, using a single engine for both land and water operations, eliminating the complexity and weight penalties associated with separate propulsion systems. The six-cylinder gasoline engine generated 94 horsepower at 3,000 revolutions per minute, providing adequate performance for both operational modes while maintaining fuel efficiency essential for sustained operations. Land propulsion utilized conventional six-wheel drive configuration, capable of 50 miles per hour maximum speed on improved roads and 35 miles per hour cross-country over varied terrain. Water propulsion employed a three-bladed propeller measuring 18 inches in diameter, enabling maximum water speed of 5.5 knots in calm conditions and maintaining effective maneuverability in currents up to 3.2 knots. Propeller design incorporated variable pitch characteristics, optimizing efficiency across different load conditions and water states. Rudder systems provided directional control during water operations, with steering response characteristics enabling precise maneuvering in confined waterways and landing areas. Vehicle construction utilized welded steel hull design, providing watertight integrity while maintaining structural strength sufficient for cargo operations and off-road movement. Hull plating measured 0.109 inches in thickness, providing protection against small arms fire, while minimizing weight penalties that might affect buoyancy and performance characteristics. Internal compartmentalization included sealed storage areas, protecting essential equipment from water damage during amphibious operations and drainage systems, enabling rapid water removal following water-to-land transition. Load-carrying specifications provided tactical flexibility essential for sustained operations across water obstacles while accommodating varied cargo types and mission requirements. Standard cargo capacity reached 5,000 pounds, distributed across a cargo area measuring 12 feet by 5.5 feet, with additional payload capacity available through specialized loading configurations. Personnel transport configuration accommodated 25 fully equipped soldiers or 12 stretcher casualties with medical attendants, providing tactical flexibility for varied operational requirements. Specialized loading procedures enabled transport of artillery pieces up to 105 mm caliber or equivalent engineering equipment weighing up to 4,800 pounds. Cargo securing systems utilized standardized tie-down points and adjustable restraining devices compatible with military cargo handling procedures. Loading and unloading operations required average times of 8.7 minutes for general cargo and 12.4 minutes for specialized equipment, enabling rapid turnaround during intensive operations. Operational range characteristics enabled sustained operations without frequent refueling requirements that might compromise operational security or tactical timing. Fuel capacity of 60 gallons provided operational range of 450 miles on improved roads or 60 miles during water operations under standard load conditions. Extended range capabilities enabled strategic movement between widely separated water crossings without requiring intermediate fuel supplies or reducing operational flexibility. Fuel consumption efficiency averaged 8.7 miles per gallon during road operations and 4.2 gallons per hour during water transit, comparing favorably with conventional vehicles operating under similar load conditions. Dual fuel capability enabled operation using either gasoline or diesel fuel depending on availability and operational requirements, providing logistical flexibility during extended operations when fuel supply chains might face disruption or capacity limitations. Crew requirements remained minimal despite the vehicle's dual operational modes, reflecting simplified control systems and reliable mechanical design that reduced training time and personnel requirements. Standard crew consisted of one operator trained in both land and water operation techniques, enabling rapid transition between operational modes without requiring specialist personnel or extensive coordination procedures. Driver training programs required 89 hours of instruction covering both operational modes, vehicle maintenance, and tactical employment procedures. Cross-training capabilities enabled any qualified motor transport operator to achieve amphibious vehicle proficiency within 3 weeks of intensive instruction, providing personnel flexibility essential for sustained operations. Training curriculum included water operation techniques, emergency procedures, navigation methods, and coordination with supporting forces. Advanced training covered night operations, adverse weather conditions, and tactical employment under enemy fire. German river crossing capabilities reflected different doctrinal approaches, emphasizing engineering solutions and specialized equipment rather than integral amphibious vehicles capable of independent operation. Standard German river crossing procedures required construction of pontoon bridges capable of supporting armored vehicles, consuming significant time and engineering resources while creating vulnerable chokepoints subject to enemy interdiction. Bridge construction typically required 4 to 8 hours for tactical bridges capable of supporting wheeled vehicles, extending to 12 to 18 hours for bridges capable of supporting armored vehicles weighing up to 45 tons. Enemy engineering units maintained inventories of specialized bridging equipment, including pontoon sections, steel decking, and anchoring systems requiring trained personnel and favorable conditions for effective deployment. Standard pontoon bridge capacity supported vehicles weighing up to 16 tons, adequate for most wheeled vehicles, but limiting options for heavier equipment, essential for sustained operations. Construction procedures required specialized engineering personnel and favorable conditions including calm water and limited enemy interference. Completed bridges remained vulnerable to artillery fire, air attack, and demolition by infiltrating forces, creating tactical vulnerabilities that affected operational planning and resource allocation. Bridge protection requirements diverted combat units from other missions while limiting tactical flexibility through concentration of forces at predictable locations. Maintenance requirements for completed bridges included continuous inspection and repair procedures, consuming engineering resources throughout operational periods. German amphibious capabilities remained limited to small numbers of specialized vehicles and equipment designed for specific tactical applications rather than general logistical support. Standard German amphibious vehicles consisted primarily of modified trucks, with waterproofing modifications enabling fording of shallow water obstacles up to 3 feet in depth. These modifications provided limited capability compared to purpose-built amphibious vehicles capable of operation in deeper water conditions without requiring extensive preparation. Swimming capabilities among German armored vehicles required extensive preparation and favorable conditions while providing limited operational capability and high risk of equipment loss. Waterproofing procedures for tanks and armored vehicles consumed significant time while requiring specialized equipment and trained personnel for effective implementation. Prepared vehicles could ford water obstacles up to 13 feet in depth using snorkel equipment, but preparation time averaged 45 minutes per vehicle with success rates of only 73% under favorable conditions. Operational limitations included reduced visibility, limited maneuverability, and vulnerability to equipment failure, resulting in vehicle loss and crew casualties. Recovery procedures for vehicles experiencing difficulties during water crossing required specialized equipment and favorable conditions, often proving impossible under combat conditions. Failure rates increased significantly during adverse weather or enemy interference, limiting tactical applications to carefully planned operations under controlled conditions. Intelligence analysis revealed that German defensive planning had not anticipated large-scale employment of amphibious vehicles capable of bypassing traditional river crossing points while maintaining full cargo capacity. Defensive preparations concentrated on bridge sites and established ferry locations, leaving intermediate areas with reduced observation and fire coverage. Anti-tank obstacles and defensive positions focused on likely bridge approaches rather than providing comprehensive coverage along extended river frontages. German defensive doctrine allocated resources based on assumptions about American crossing capabilities that proved inadequate when confronted with large-scale amphibious vehicle employment. Resource allocation concentrated defensive strength at predicted crossing points while accepting risk in areas considered impassable for sustained logistical operations. This allocation pattern created vulnerabilities that amphibious operations could exploit through selection of undefended crossing sites. American amphibious vehicle employment enabled tactical surprise through utilization of crossing sites that defending forces had not prepared for major operations while maintaining full logistical support capability. Vehicle capabilities permitted selection of crossing points based on tactical advantage rather than limitations imposed by bridging equipment or established ferry sites. This operational flexibility complicated enemy defensive planning while providing attacking forces with initiative in selecting engagement conditions and operational timing. Production efficiency reflected systematic application of mass production techniques, adapted from civilian automotive manufacturing, while incorporating specialized requirements for amphibious operations. Direct labor requirements totaled 247 man-hours per completed vehicle, representing efficient utilization of skilled workers and assembly line procedures. Indirect labor allocation added 78 man-hours for support functions, including quality control, materials handling, and administrative oversight essential for maintaining production standards. Total production cost averaged $8,600 per vehicle, including all components, testing, and delivery expenses, comparing favorably with specialized watercraft of equivalent capacity while providing dual-mode operational capability. Cost analysis included raw materials, labor, overhead, and testing expenses across complete production cycles. Economies of scale reduced unit costs by 34% compared to initial production estimates based on smaller production quantities. Material allocation demonstrated efficient utilization of strategic resources during periods of competing military and civilian requirements while maintaining essential performance characteristics. Each vehicle consumed 4.2 tons of steel, 340 pounds of aluminum for engine components, and 180 pounds of copper for electrical systems and propulsion equipment. Rubber requirements totaled 280 pounds per vehicle for tires, seals, and electrical insulation, representing efficient allocation of critical materials subject to wartime rationing. Conservation measures reduced material consumption by 23% compared to initial design specifications, while maintaining operational capabilities essential for combat effectiveness. Design modifications included weight reduction techniques, alternative materials substitution, and manufacturing process improvements that maintain performance while reducing resource requirements. Material savings enabled increased production rates without requiring additional resource allocation or compromising other military programs. Quality control procedures maintained consistent performance standards throughout the production program, while accommodating accelerated production schedules essential for operational requirements. Waterproofing tests verified hull integrity under pressures equivalent to 7-foot water depth, ensuring operational capability under maximum design conditions, with safety margins adequate for combat operations. Engine performance testing validated power output and fuel consumption characteristics under both land and water operational modes. Transmission testing confirmed reliability during transition between operational modes under varied load conditions and operational stress levels. Durability testing included extended operation under simulated combat conditions, with maintenance intervals consistent with field operations. Performance validation confirmed design specifications while identifying potential improvements incorporated into subsequent production batches. Component standardization enabled efficient maintenance and parts supply throughout global deployment, while reducing training requirements and inventory complexity. Engine specifications shared 78% commonality with existing truck engines, simplifying maintenance procedures and parts inventory requirements for field units. Transmission components utilized proven designs from automotive applications, ensuring reliability and availability of replacement parts through existing supply chains. Electrical systems incorporated standard military components compatible with other vehicle types, reducing training requirements and inventory complexity, while ensuring reliability under combat conditions. Communication equipment utilized standard military radio systems with waterproof modifications enabling operation during amphibious phases. Lighting systems included blackout capability and infrared compatibility for night operations under tactical conditions. Tactical employment doctrine reflected the unique capabilities provided by integral amphibious vehicles in combined arms operations, while accommodating limitations imposed by operational conditions. Standard procedures integrated amphibious vehicles with conventional river crossing operations, providing sustained supply capability, independent of bridge construction or ferry operations. Vehicle employment enabled continuous logistical support during initial phases of river crossing operations, when bridge construction remained incomplete or vulnerable to enemy interdiction. Operational planning incorporated amphibious vehicle capabilities into comprehensive river crossing schemes, enabling multiple crossing sites and reducing dependence on single points of failure that might compromise entire operations. Vehicle deployment provided tactical commanders with flexibility in selecting crossing sites based on enemy dispositions rather than limitations imposed by conventional crossing equipment. Multiple crossing capability complicated enemy defensive planning while providing redundant supply routes essential for sustained operations. Supply chain efficiency enabled sustained operations across extended river obstacles without requiring intermediate supply dumps or transshipment facilities that might create vulnerabilities or logistical bottlenecks. Vehicle capabilities permitted direct movement of supplies from rear area depots to forward combat units without breaking bulk or requiring specialized handling equipment. This end-to-end capability reduced handling time by 67% compared to conventional supply methods requiring multiple transshipment operations. Load-carrying versatility provided tactical flexibility, essential for rapid response to changing operational requirements, while maintaining logistical efficiency. Standard configurations included general cargo, personnel transport, medical evacuation, and specialized equipment movement, with reconfiguration procedures requiring minimal time and equipment. Loading procedures accommodated standard military containers and palletized cargo without requiring specialized handling equipment or extensive crew training. Medical evacuation capabilities provided enhanced casualty care during river crossing operations, when conventional evacuation routes might become disrupted by enemy action or operational conditions. Vehicle configuration accommodated up to 12 stretcher patients with medical attendants, enabling rapid evacuation from forward positions to medical facilities located across water obstacles. Medical equipment mounting provisions enabled transport of specialized medical devices and treatment equipment required for advanced care during evacuation procedures. German defensive doctrine had not anticipated the employment of vehicles capable of sustained cargo operations across major water obstacles without requiring specialized port facilities or landing areas prepared by engineering units. Traditional defensive planning focused on controlling bridge sites and ferry locations, while accepting reduced coverage of intermediate areas considered impassable for wheeled vehicles carrying significant loads. This defensive approach created vulnerabilities that amphibious vehicles could exploit through utilization of undefended crossing sites. Enemy anti-tank defenses concentrated along likely vehicle approaches from established crossing points, creating defensive gaps in areas where conventional vehicles could not operate, but amphibious vehicles could achieve surprise. Anti-tank gun positions provided overlapping coverage of bridge approaches, but left extended frontages inadequately covered against vehicles capable of independent water crossing. Defensive planning assumptions proved inadequate when confronted with vehicles capable of selecting crossing sites based on tactical advantage rather than engineering limitations. Minefield employment followed similar patterns, creating obstacles at likely chokepoints while leaving alternative routes available for amphibious operations that could bypass traditional crossing points. Existing mine stocks required allocation between traditional defensive positions and extended coverage of potential amphibious landing areas, reducing defensive effectiveness at established positions. Mine laying capacity proved insufficient for comprehensive coverage of extended frontages vulnerable to amphibious assault. Observation and fire control systems focused on established crossing sites where enemy planners expected major operations to develop, leaving alternative areas with reduced surveillance capability. Artillery registration concentrated on bridge sites and ferry locations, providing limited coverage of alternative crossing areas where amphibious operations might develop. Communication systems linked observation posts at traditional crossing points but provided reduced coverage of extended frontages where amphibious operations could achieve tactical surprise. Intelligence collection efforts had not identified the scale of American amphibious vehicle production or deployment, contributing to defensive planning failures and resource allocation decisions based on incomplete information. German intelligence estimates significantly underestimated both the numbers of vehicles available and their operational capabilities, preventing appropriate defensive adjustments. Intelligence failure extended to tactical characteristics including load-carrying capacity, operational range, and deployment flexibility. This intelligence failure prevented appropriate defensive adjustments that might have countered the tactical advantages provided by amphibious capabilities through alternative resource allocation or tactical modifications. German defensive planning continued to emphasize traditional crossing points while lacking adequate information about American capabilities that could bypass these defended areas. Resource constraints limited defensive adaptation even when intelligence identified potential vulnerabilities. American operational security measures contributed to the surprise achieved through amphibious vehicle employment, while protecting information essential for tactical success. Vehicle deployment utilized deception plans and movement procedures designed to conceal the scale and timing of amphibious operations from enemy intelligence collection efforts. Staging areas remained dispersed and camouflaged, preventing enemy reconnaissance from accurately assessing American capabilities and intentions. Deception operations included false radio traffic, dummy equipment deployments, and misleading logistical activities designed to focus enemy attention on areas away from actual crossing sites. Communication security procedures prevented enemy signals intelligence from identifying amphibious vehicle concentrations or operational planning. Personnel security measures restricted access to operational information, while maintaining security of deployment schedules and tactical procedures. Training programs prepared crews for employment under varied conditions including night operations, adverse weather, and enemy interference while maintaining operational effectiveness. Night operation procedures utilized infrared driving aids and sound discipline techniques, enabling covert movement during darkness. Blackout driving techniques enabled tactical movement without revealing vehicle positions to enemy observers, while maintaining navigation accuracy essential for successful operations. Adverse weather training included operation in rough water conditions and reduced visibility situations common during spring weather conditions, when river crossings typically occurred. Crew training emphasized emergency procedures including vehicle recovery, water survival techniques, and coordination with rescue operations. Cold weather operation procedures addressed equipment reliability and crew protection during operations in adverse conditions. Maintenance procedures reflected the robust design characteristics incorporated throughout vehicle systems, while accommodating field conditions and limited maintenance facilities. Field maintenance requirements averaged 2.7 hours per vehicle per week during active operations, comparing favorably with conventional vehicles operating under similar conditions. Parts commonality with standard vehicle types enabled depot-level maintenance using existing facilities and trained personnel without requiring specialized equipment or extensive retraining. Preventive maintenance schedules optimized vehicle reliability while minimizing operational disruption through efficient scheduling and standardized procedures. Daily maintenance procedures required 23 minutes per vehicle covering essential systems inspection, lubrication, and fluid level checks. Weekly maintenance extended 2.4 hours covering more comprehensive system inspection and minor component replacement as required. Monthly maintenance procedures required 6.8 hours for major system inspection and component replacement following manufacturer recommendations and field experience data. Maintenance training programs qualified personnel in all vehicle systems while emphasizing field expedient repair techniques using available materials and tools. Crew-level maintenance capabilities enabled resolution of 87% of minor mechanical problems without requiring specialized maintenance support. Fuel logistics benefited from dual-fuel capability, enabling operation using either gasoline or diesel fuel, depending on availability and operational requirements, while maintaining performance characteristics. Fuel consumption characteristics provided operational range adequate for tactical missions without requiring frequent refueling that might compromise operational security or reveal vehicle positions to enemy forces. Fuel efficiency during water operations averaged 4.2 gallons per hour, enabling sustained operations across extended water obstacles. Fuel storage and handling procedures accommodated both fuel types, while ensuring supply flexibility during extended operations when specific fuel types might become unavailable. Fuel consumption planning incorporated operational profiles including water transit time, land movement requirements, and operational reserves essential for mission completion. Supply planning addressed fuel availability at forward locations while maintaining security of supply operations. Communication equipment installation enabled coordination with higher headquarters and supporting units during both land and water operations, while maintaining tactical security. Radio systems maintained contact ranges up to 12 miles using standard antenna configurations, providing communication capability adequate for tactical coordination and operational reporting. Waterproofing procedures protected communication equipment during water operations while maintaining full operational capability. Radio operation procedures included frequency management, communication security protocols, and coordination with supporting units during combined operations. Antenna systems incorporated removable configurations, enabling rapid transition between land and water operations without compromising communication capability. Backup communication systems provided redundant capability essential for critical operations when primary systems might experience failure or enemy interference. Navigation equipment included compass systems and basic navigation aids essential for water operations, where traditional landmarks might not be available or reliable. Dead reckoning capabilities enabled navigation during limited visibility conditions, common during early morning or evening operations, when tactical conditions might require movement during reduced visibility periods. Navigation training prepared crews for operation in unfamiliar areas where conventional road networks might not provide adequate guidance. Water navigation techniques included current compensation, drift calculation, and landing site identification, using available landmarks and tactical references. Navigation planning incorporated tide schedules, current patterns, and weather conditions affecting water operations. Emergency navigation procedures addressed equipment failure scenarios while maintaining operational capability essential for mission completion. German river crossing equipment reflected engineering approaches requiring significant time and specialized personnel for deployment and operation, while creating vulnerable chokepoints during construction and operation phases. Standard German pontoon bridges required 4 to 8 hours for construction, using specialized engineering units and favorable conditions including calm water and limited enemy interference. Bridge capacity limitations restricted vehicle types and loading that could utilize completed structures, creating operational bottlenecks during intensive operations. Construction procedures required coordination between multiple engineering units, while maintaining security against enemy interference during vulnerable construction phases. Material requirements included pontoon sections, decking, anchoring equipment, and specialized tools transported to bridge sites, using limited transportation capacity. Personnel requirements included trained bridge construction specialists, whose availability limited bridge construction capability. Ferry operations provided limited capacity and required favorable weather conditions for effective operation while remaining vulnerable to enemy fire and equipment failure. Standard German ferries accommodated 4-wheeled vehicles or 2 armored vehicles per trip, creating significant time delays for large-scale movements requiring extensive vehicle transportation. Ferry operations remained vulnerable to enemy fire and required protection from supporting units, further reducing operational efficiency. Ferry maintenance requirements included continuous inspection and repair procedures, while operating under tactical conditions that might limit maintenance capability. Fuel requirements for ferry operations competed with other operational priorities while limiting operational duration. Personnel requirements for ferry operations included trained operators and maintenance personnel whose availability affected operational capability. Specialized German amphibious vehicles remained limited in numbers and capabilities compared to purpose-built amphibious cargo vehicles capable of sustained operations across extended water obstacles. Existing German amphibious capabilities focused on reconnaissance and specialized operations rather than sustained cargo movement essential for logistical support. Production numbers remained limited due to competing priorities and resource constraints, affecting German industrial capacity throughout the war period. Development programs for German amphibious vehicles faced resource limitations and competing priorities that prevented comprehensive development and production adequate for operational requirements. Manufacturing capacity remained devoted to other vehicle programs considered higher priority, limiting amphibious vehicle availability. Design approaches emphasized specialized performance rather than versatility and reliability essential for sustained operations. American amphibious vehicle production reflected industrial capacity and resource allocation that German planners had not anticipated when developing defensive strategies or assessing American capabilities. Monthly production rates of 583 vehicles during peak periods provided tactical capabilities that significantly exceeded German estimates of American amphibious capacity. Total production of 21,247 vehicles created strategic reserves that enabled sustained operations across multiple theater commands simultaneously. Production scheduling enabled delivery of vehicles according to operational requirements, while maintaining quality standards essential for combat effectiveness. Manufacturing facilities operated around-the-clock schedules using 3-shift operations that maximized production capacity. Worker training programs maintained skilled labor availability while accommodating production expansion requirements. Deployment patterns reflected systematic planning for sustained operations, requiring continuous supply across major water obstacles, while maintaining tactical flexibility. Vehicle allocation provided adequate capacity for supporting full-scale offensive operations without requiring reduction in other operational capabilities. Reserve capacity enabled absorption of combat losses while maintaining operational effectiveness essential for sustained offensive operations. Strategic distribution allocated amphibious vehicles across multiple theater commands, while maintaining adequate reserves for unexpected operational requirements. Transportation networks enabled rapid redeployment of vehicles between threatened areas while maintaining operational security. Maintenance support accompanied vehicle deployments, ensuring sustained operational capability throughout extended operations. Operational effectiveness demonstrated the tactical advantages achieved through technological innovation and industrial capacity, while validating design concepts and tactical employment procedures. Combat loss rates averaged 3.4% per major operation, indicating both the effectiveness of the vehicles and the tactical surprise achieved through their employment. Replacement capacity enabled restoration of unit strength within 48 hours of sustaining losses, maintaining operational continuity essential for sustained offensive operations. Performance analysis confirmed design specifications under combat conditions, while identifying areas for potential improvement in subsequent production batches. Reliability statistics exceeded design targets with 94% operational availability during intensive operations. Crew performance evaluations validated training programs, while identifying additional training requirements for optimal vehicle employment. Logistical impact extended beyond immediate tactical applications to influence strategic planning and resource allocation throughout theater operations, while reducing dependence on vulnerable infrastructure. Reduced dependence on vulnerable bridge structures enabled operational planning based on tactical considerations rather than limitations imposed by crossing equipment availability. Enhanced supply flexibility provided strategic reserve capabilities essential for exploiting tactical successes and maintaining operational momentum. Supply chain efficiency enabled sustained operations without requiring extensive intermediate storage facilities or transshipment operations that might create vulnerabilities. Direct supply delivery from rear areas to forward combat units reduced handling time and personnel requirements while improving supply security. Operational flexibility enabled rapid response to changing supply requirements without requiring extensive logistical reorganization. Strategic surprise achieved through amphibious vehicle employment contributed to broader operational success by complicating enemy defensive planning and resource allocation across extended frontages. German forces required reallocation of defensive resources to cover extended frontages previously considered impassable for sustained operations. This resource reallocation reduced defensive effectiveness at traditional crossing sites while creating opportunities for exploitation through multiple avenues of approach. Defensive resource allocation required German forces to spread limited assets across extended frontages without achieving adequate defensive density at any single location. Anti-tank weapon distribution provided insufficient coverage for comprehensive defense while reducing concentration of defensive fires. Personnel allocation created gaps in defensive coverage while reducing reserve availability for counterattack operations. Intelligence analysis revealed systematic German underestimation of American technological capabilities and industrial capacity, supporting advanced military equipment development programs. German planning assumptions reflected limited understanding of American production capacity and technological innovation in specialized military applications. Intelligence failure extended to tactical capabilities, deployment schedules, and operational employment procedures essential for effective defensive planning. This intelligence failure contributed to defensive preparations inadequate for countering American technological advantages while misallocating limited German resources. German defensive planning continued to emphasize traditional approaches inadequate for countering American innovations. Resource constraints prevented adequate defensive adaptations, even when intelligence identified potential vulnerabilities. American technological development programs reflected systematic approaches to identifying and solving tactical problems through engineering innovation and industrial application, while utilizing existing technological capabilities. Amphibious vehicle development represented one element of comprehensive programs, addressing identified operational limitations and tactical vulnerabilities. Integration of civilian technological capabilities with military requirements enabled rapid development and production of effective solutions to tactical problems. Development procedures utilized proven engineering approaches while incorporating innovations essential for amphibious operations. Testing programs validated design concepts under operational conditions before full-scale production commitments. Performance evaluation confirmed operational capabilities, while identifying potential improvements for subsequent development programs. Industrial coordination between military requirements and civilian manufacturing capacity enabled rapid scaling of production to meet strategic requirements while maintaining quality standards. Existing automotive manufacturing facilities provided technological base and production capacity essential for rapid program implementation. Skilled workforce availability and established supply chains enabled efficient production without requiring extensive infrastructure development or worker training programs. Manufacturing integration utilized existing production lines while incorporating specialized equipment essential for amphibious vehicle assembly. Quality control procedures adapted automotive industry standards for military applications while maintaining production efficiency. Supply chain coordination ensured adequate component availability while accommodating production schedule requirements. Component integration reflected systematic engineering approaches, utilizing proven technologies in new applications, rather than developing entirely new systems requiring extensive testing and development time. Engine and transmission systems utilized proven automotive technologies adapted for amphibious applications, ensuring reliability while reducing development time and cost. Hull construction techniques incorporated shipbuilding practices adapted for mass production using automotive manufacturing methods. Testing procedures validated component performance under amphibious conditions while ensuring compatibility with existing automotive systems. Integration testing confirmed operational capability across varied conditions while identifying potential improvements. Performance validation confirmed design specifications while ensuring reliability under combat conditions. Testing and evaluation programs validated vehicle performance under operational conditions before full-scale production commitments while identifying potential improvements. Prototype testing included extended operations under varied conditions, including rough water, adverse weather, and intensive operational schedules. Performance validation confirmed design specifications and identified potential improvements incorporated into production vehicles. Operational testing included tactical employment under simulated combat conditions, while evaluating crew performance and maintenance requirements. Performance analysis validated training programs, while identifying additional requirements for optimal vehicle employment. Reliability testing confirmed mechanical systems performance under intensive operational conditions. User training programs prepared crews for effective employment under tactical conditions, including enemy interference and operational stress, while maintaining safety standards. Training curriculum addressed both technical operation procedures and tactical employment techniques, essential for effective integration with combined arms operations. Standardized training materials enabled efficient instruction across multiple training facilities while maintaining consistent performance standards. Advanced training covered specialized techniques including night operations, adverse weather conditions, and tactical coordination with supporting forces. Emergency procedures training addressed vehicle recovery, crew survival, and coordination with rescue operations. Maintenance training qualified crews in field service procedures, while emphasizing preventive maintenance essential for operational reliability. German defensive adaptations following initial contact with American amphibious vehicles indicated recognition of the tactical challenge presented by these capabilities, while revealing resource limitations preventing comprehensive countermeasures. Defensive modifications included increased patrolling along river frontages and establishment of observation posts covering previously unmonitored areas. However, resource limitations prevented comprehensive defensive coverage of extended frontages vulnerable to amphibious operations. Anti-tank weapon deployment expanded to cover alternative crossing sites where amphibious vehicles might operate, but weapon availability remained insufficient for comprehensive coverage, while reducing defensive concentration at traditional crossing sites. Existing anti-tank weapons proved effective against amphibious vehicles when properly positioned, but deployment limitations created defensive gaps exploitable through tactical planning and operational coordination. Minefield employment expanded to cover likely landing sites for amphibious operations, but mine availability and emplacement time limitations prevented comprehensive obstacle coverage while reducing defensive effectiveness at traditional positions. Existing mine stocks required allocation between traditional defensive positions and extended coverage of amphibious landing areas. Mine-laying capacity proved insufficient for covering extended frontages while maintaining defensive density. Communication system modifications attempted to provide improved coverage of extended defensive frontages, but equipment limitations prevented comprehensive surveillance of all potential crossing sites, while reducing communication effectiveness at established positions. Radio networks expanded to include additional observation posts, but communication range and equipment availability limited effectiveness of extended surveillance systems. Artillery support procedures incorporated target registration for potential amphibious landing sites, but ammunition constraints prevented comprehensive coverage of all potential crossing areas, while reducing fire concentration available for primary defensive missions. Existing artillery units required allocation between traditional defensive fires and expanded coverage of amphibious threats. Fire coordination procedures adapted to address multiple potential crossing sites, while maintaining responsive fires for established defensive positions. American operational planning incorporated intelligence assessments of German defensive capabilities and limitations, enabling selection of crossing sites, offering maximum tactical advantage while minimizing operational risks. Intelligence analysis identified defensive gaps and resource limitations that amphibious operations could exploit through appropriate tactical planning. Operational timing coordinated amphibious operations with conventional crossing operations to maximize tactical surprise and enemy confusion. Planning procedures incorporated multiple crossing sites, while coordinating with supporting operations to achieve maximum tactical effect. Deception operations contributed to operational success while protecting actual crossing sites from enemy attention. Coordination with supporting forces enhanced amphibious operations while providing mutual support during vulnerable operational phases. Deception operations contributed to tactical surprise by concealing the scale and timing of amphibious operations while suggesting alternative crossing sites and operational timing to enemy intelligence services. Deception plans included false radio traffic, dummy equipment deployments, and misleading logistical activities designed to focus enemy attention on areas away from actual crossing sites. Communication deception included simulated planning activities and false operational schedules. Electronic deception procedures utilized radio traffic patterns, suggesting alternative operational plans while concealing actual deployment schedules. Physical deception included dummy vehicle concentrations and simulated preparation activities at false crossing sites. Operational security procedures protected actual plans while supporting deception activities designed to confuse enemy intelligence assessment. Coordination with supporting arms enhanced amphibious vehicle effectiveness through integrated fire support and air cover during vulnerable operational phases while maintaining tactical security. Artillery support included counter-battery fires against enemy positions, threatening crossing sites, and suppressive fires during critical phases of amphibious operations. Fire coordination procedures enabled responsive support while maintaining ammunition conservation essential for sustained operations. Air support provided reconnaissance of crossing sites and close support during vulnerable transition phases from water to land operations. Air coordination included suppression of enemy observation posts and interdiction of enemy reinforcements threatening amphibious operations. Close air support procedures addressed the unique requirements of amphibious operations while maintaining tactical coordination. Combat engineering support enhanced crossing site preparation and obstacle clearance, essential for effective amphibious operations while maintaining operational security. Engineering units provided reconnaissance of potential crossing sites and prepared landing areas for optimal vehicle transition from water to land operations. Site preparation included obstacle clearance, route marking, and establishment of vehicle marshalling areas. Obstacle clearance included removal of anti-tank obstacles and mine clearance operations protecting amphibious landing areas while maintaining tactical surprise. Engineering coordination addressed the specialized requirements of amphibious operations while providing support for subsequent operations. Emergency repair capabilities addressed vehicle recovery and route maintenance essential for sustained operations. Supply coordination ensured adequate fuel, ammunition, and maintenance support for sustained amphibious operations across extended water obstacles while maintaining logistical security. Supply planning incorporated the unique requirements of amphibious vehicles, including specialized maintenance procedures and parts requirements different from conventional vehicles. Forward supply arrangements enabled sustained operations without requiring return to rear areas for routine maintenance or resupply. Fuel supply procedures addressed dual fuel capability, while ensuring adequate reserves for extended operations. Ammunition resupply included specialized requirements for amphibious operations, while maintaining supply security. Part supply addressed the unique maintenance requirements of amphibious vehicles while utilizing existing supply chains for common components. Medical support arrangements addressed the unique requirements of casualties sustained during amphibious operations, including water-related injuries and evacuation challenges, while maintaining treatment standards. Medical evacuation procedures utilized amphibious vehicles as primary evacuation platforms when conventional evacuation routes remained unavailable due to incomplete bridge construction or enemy interference. Treatment protocols addressed injuries common during amphibious operations while maintaining medical standards. Casualty collection procedures addressed the challenges of medical evacuation during water operations while ensuring rapid treatment of injured personnel. Medical equipment transportation utilized amphibious vehicles for moving medical supplies and equipment across water obstacles. Medical coordination addressed the specialized requirements of amphibious operations while maintaining integration with conventional medical support. Tactical integration with conventional forces enabled coordinated operations, utilizing both amphibious and conventional crossing capabilities to maximize operational effectiveness while maintaining tactical flexibility. Combined operations complicated enemy defensive planning while providing redundant capabilities essential for sustained offensive operations. Tactical coordination enabled mutual support between amphibious and conventional forces during vulnerable phases of river crossing operations. Operational coordination addressed timing and resource allocation while maintaining tactical surprise essential for successful operations. Command and control procedures enabled effective coordination while maintaining operational security. Intelligence sharing enhanced tactical planning while protecting operational information from enemy collection efforts. Operational security procedures protected information about amphibious vehicle capabilities and deployment plans from enemy intelligence collection efforts, while maintaining essential coordination. Security measures included restricted access to staging areas, communication security procedures, and personnel screening for units involved in amphibious operations. Operational security contributed to tactical surprise, essential for successful employment of amphibious capabilities. Communication security prevented enemy signals intelligence from identifying amphibious vehicle concentrations or operational timing. Physical security protected staging areas and equipment from enemy observation while maintaining operational readiness. Personnel security procedures ensured reliability of personnel involved in sensitive operations while maintaining operational effectiveness. Strategic assessment revealed the cumulative impact of amphibious vehicle capabilities on German defensive planning and resource allocation throughout the Western Theater. While demonstrating technological advantages, German forces required reallocation of limited resources to address amphibious threats, reducing effectiveness of defenses at traditional crossing sites while creating resource allocation dilemmas. Resource constraints prevented comprehensive defensive adaptations adequate for countering American amphibious capabilities. Theater-level effects included systematic degradation of German defensive effectiveness, while forcing resource allocation decisions that reduced overall defensive capability. Strategic implications extended beyond immediate tactical effects to influence German operational planning and strategic decision-making. Long-term effects included recognition of American technological superiority and industrial capacity advantages. Enemy morale factors reflected the psychological impact of unexpected American capabilities that German defensive planning had not anticipated while demonstrating intelligence failures. Surprise employment of amphibious vehicles contributed to defensive uncertainty and reduced confidence in existing defensive preparations. Psychological effects extended beyond immediate tactical impact to influence broader German assessment of American technological and industrial capabilities. Morale impact included reduced confidence in defensive preparations, while increasing uncertainty about American capabilities and intentions. Strategic psychological effects influenced German strategic planning, while contributing to defensive orientation that reduced operational initiative. Cumulative psychological impact contributed to broader recognition of American technological and industrial advantages. Intelligence failure analysis indicated systematic German underestimation of American industrial capacity and technological innovation in military applications, while revealing intelligence collection limitations. German intelligence services failed to identify the scale of American amphibious vehicle production or accurately assess their operational capabilities. Intelligence failure extended to tactical employment procedures and operational capabilities essential for effective defensive planning. Collection failures included inadequate technical intelligence about vehicle capabilities and production schedules, while missing deployment patterns and operational procedures. Analysis failures included incorrect assessment of American industrial capacity and technological development programs. Intelligence distribution failed to provide tactical commanders with adequate information for defensive planning. Industrial comparison revealed fundamental differences in American and German approaches to military vehicle development and production, while highlighting resource allocation advantages. American programs emphasized mass production of versatile vehicles using standardized components and proven technologies while maintaining quality standards. German approaches focused on specialized vehicles with advanced capabilities but limited production capacity, reflecting resource constraints and competing priorities. Production efficiency differences enabled American forces to sustain operations requiring continuous equipment replacement and expansion, while German production remained constrained by resource limitations. Manufacturing approach differences reflected industrial capacity advantages, while demonstrating systematic approaches to military equipment development. Resource allocation patterns revealed strategic priority differences affecting military equipment programs. Technological innovation patterns demonstrated American advantages in integrating civilian industrial capabilities with military requirements for rapid development and production of effective military equipment while utilizing existing technological resources. American programs utilized existing automotive and maritime technologies in new applications, enabling rapid development without extensive research and development programs. German technological development remained constrained by resource limitations and competing military priorities. Innovation approaches reflected fundamental differences in industrial organization and resource availability, while demonstrating systematic development procedures. Integration capabilities enabled rapid adaptation of civilian technologies for military applications while maintaining quality standards. Development efficiency enabled rapid program completion while meeting operational requirements. Production efficiency analysis revealed American advantages in mass production techniques and industrial coordination, essential for sustained military equipment production while maintaining quality control. American programs achieved production rates that German industry could not match due to resource limitations and competing production requirements. Industrial capacity differences enabled American forces to sustain operations requiring continuous equipment, replacement, and expansion. Manufacturing organization enabled efficient production while maintaining quality standards essential for combat effectiveness. Production coordination utilized existing industrial capacity while adapting civilian manufacturing techniques for military applications. Efficiency advantages enabled resource allocation to multiple programs while maintaining individual program effectiveness. Resource allocation patterns demonstrated fundamental differences in American and German strategic priorities, affecting military equipment, development, and production, while revealing industrial capacity advantages. American programs received adequate resources for full development and production cycles, enabling effective solutions to identified tactical problems. German programs faced resource constraints, requiring compromises in development and production that reduced operational effectiveness. Strategic priority differences affected resource allocation decisions while influencing military equipment development programs. Industrial capacity limitations prevented German programs from achieving adequate production levels, while competing priorities reduced resource availability. Resource allocation efficiency enabled American programs to achieve operational objectives while maintaining program effectiveness. Strategic implications extended beyond immediate tactical applications to influence broader patterns of military innovation and industrial mobilization, while demonstrating technological advantages. American success in developing and producing effective amphibious vehicles demonstrated the strategic advantages achieved through comprehensive industrial mobilization and technological innovation. German inability to match American capabilities reflected structural limitations in industrial capacity and resource allocation, affecting multiple military programs. Long-term strategic effects influenced post-war military development while validating systematic approaches to military innovation. Industrial mobilization patterns demonstrated the importance of civilian industrial capacity in military equipment development, while highlighting technological integration advantages. Strategic planning implications affected post-war military doctrine and equipment development priorities. Long-term effects influenced post-war military vehicle development and amphibious operations doctrine throughout multiple nations and military services, while validating design approaches. American amphibious vehicle success validated design approaches, emphasizing versatility and reliability over specialized performance characteristics. International military services adopted similar approaches in subsequent vehicle development programs based on American operational experience. Doctrinal effects included recognition of amphibious vehicle capabilities in river crossing operations, while influencing tactical procedures and operational planning. Equipment development programs incorporated lessons learned from American amphibious vehicle employment while adapting design approaches for different operational requirements. Training programs adopted American procedures while modifying techniques for specific operational conditions. Operational lessons learned from amphibious vehicle employment influenced broader tactical doctrine and combined arms procedures for river crossing operations while validating integrated approaches. American experience demonstrated the effectiveness of integrated amphibious capabilities in reducing dependence on vulnerable bridge structures and expanding tactical options for offensive operations. These lessons influenced post-war military doctrine and equipment development programs across multiple military services. Tactical innovation demonstrated the importance of technological integration in military operations, while highlighting the advantages of versatile equipment design. Combined arms procedures incorporated amphibious vehicle capabilities while maintaining coordination with conventional forces. Operational procedures validated systematic approaches to river crossing operations while reducing dependence on vulnerable infrastructure. The American development of integral amphibious cargo vehicles created tactical capabilities that German defensive planning had not anticipated, enabling sustained supply operations across major water obstacles without requiring vulnerable bridge construction or limited ferry capacity, while achieving strategic surprise through employment of technological advantages that enemy intelligence services had failed to identify accurately. Industrial production of 21,247 vehicles provided strategic reserves adequate for sustained operations across multiple theater commands simultaneously.